Yet another Mars event. Today we're going to be talking about autonomous navigation, presented by the one and only Thien-Minh. He has recently joined UQ. He's going to be a lecturer for mechatronics, so you might run into him in your degree. I'll give it away to him.
Thank you, everybody. So I see a few familiar faces here. See Miguel here, and then you at 2800. If the powers that be design so.
Just swap that one with this if you don't mind.
This one?
Yeah. Excellent.
Yeah. Agenda. So first I'm going to maybe have a few slides to talk about my identity as a researcher. The society is important. And then we're talking about my PhD for the first 5 years, and then maybe 2 years into my postdoctoral research. Then afterwards, I'm going to talk about the late stage of my postdoc and how I apply the job here, and then what I'm going to do next at UQ. So then you see the title here. The first one is my work. The second one is how I focus on the sensors. And the third one is how I'm going to use the prior information for the autonomy. So that's me. And if I'm summarizing my work here, you can see some kind of diagram where I have two main tracks. So if you consider a robot that navigates in the world, it's not going to need some kind of control strategy, right? So that's actually what I worked on my PhD and as a mentor in my postdoc to junior students. And then my work during my PhD was on unmanned aerial vehicles. So I worked on drones. I flew 10 UAVs at the time. We crashed also 10 UAVs at the time. We had that. And then I moved on to work on collaborative algorithms to coordinate between the UAVs to achieve some certain swarm behaviors. And moving on, we develop heterogeneous capabilities between the UAVs to do inspection and other types of missions. Then when I finished my PhD, I had this conclusion. Okay, I've been doing control engineering for a while, and then every time we come up with a control law, we can always guarantee that it's going to converge or have stability perfect. But then the sensor screwed up. The sensor will mess up your day. So I say, in our team, we never had a guy who works on sensor fusion and SLAM, simultaneous localization and mapping. So that's why I spent maybe the last 4 years or something after PhD to work on SLAM. And it actually grew and grew to be the bulk of my research, as in now I'm an editor, associate editor of Robotics Automation Letters in that area of localization and mapping. And for my job application at UQ, I actually presented my work on continuous time sensor fusion, where I came up with a mathematical framework to fuse all types of sensors. And then you can see in this, along the way where I worked on the sensors, I realized that, okay, if we only focus on how to integrate the sensors at this one session, it's just going to last this session. But if you can use that data for the next sessions, your autonomous robots can actually make better decisions. It doesn't have to be subject to the certain kind of dynamics and ambient in the environment, where you can actually have information captured in a map or in some other types of prior knowledge to actually inform the robot how to make decisions. So that's where I draw the line, and the line here is basically based on my IEEE and CBPR work. You know IEEE? Does anybody know IEEE? It's the flagship conference of Robotics and Automation Society. So it's basically the where you go to find a job in robotics. CBBI is the flagship conference of computer vision. So it's the place where you go to find a job in computer vision. And then these two works, I got like some work papers here. That's like how I actually secured a job. Okay, so talking a little bit about Robotics Automation Society. I guess so far, does anybody know about Robotics and Automation Society? Like Miguel, how much do you know about our society? Are you a member? So basically, I started as a like automation and control engineer, and then I went to Singapore NTU to do PhD. And in 2017, the IEEE happened at Singapore. We didn't have any paper. Everybody was disappointed because we couldn't go to that conference. And then I learned about this society, and I realized it's the go-to place for the frontier of robotics and automation research. And if you look into the venues of robotics like publications in Journal Citation Report, that's the most authoritative list. You can see that Robotic Automation Society actually publishes the most, has the most in the Q1 one. Basically, they have 48 journals, so the first 12 would have 3 of IES. And if you go to Google Scholar, and then you search Google Scholar Robotics, they're going to give you this list of venues. Anything below number 10 is already negligible, but anything above number 10, you should know where to look for in terms of like progresses, or who's doing what to actually be relevant, right? And then you'll see that our IIS sponsored venues actually top the places. I'm actually an editor of Robotics and Automation letters. Right? So basically, it's number 1 here in the. This one measures how much activity. I mean, this one is more on the activity. This one is more on the prestige. So as you can see, the Robotics Automation is actually a very active society, and we publish it most. So now we get to the technical part, and we were going to talk about how I actually exploited sensors. I guess here we don't have a course on sensors, right? In UQ we don't have a course on sensors. I think the most relevant one you have is Tyson's course on control implementation. He teaches you GNSS and LiDAR, right? I wouldn't consider it control per se. It's basically another subclass of engineering automation, but control, you can actually put it in control because if you don't distance yourself from sensors, that's okay. And for my PhD research, I worked on this sensor that measures the distance between the UAVs, right? And then I came up with algorithms to actually exploit this information. So I don't know, Tyson never introduced this one to you, right? I had this talk with Tyson the other day. So if you actually, I give you a sensor, actually Tyson gave me a sensor once, and I asked him what is the equation of this LiDAR that you're talking about. He was very passionate about this Doppler effect LiDAR, and he's talking about all of the physics. I said, Tyson, can you just summarize this equation for me? And then if you're going home today, I think this is, I would recommend that you remember this only equation. So for whatever sensors, you basically just ignore, engineering aspects and then say, because you're going to use it, right? You're going to say, what is the information I want to exploit? What is the information I want to extract from this sensor? This is the X here. What you're going to observe from this sensor, this is the Z here, right? For LiDAR, it's going to give you the point cloud. For ultra-wideband, it's going to give you the distance. For IMU, it's going to give you the gyroscope and the accelerometer data, right? Prior information is here. It's somewhere on ways you actually don't know. For example, if it's a LiDAR, you would want to know what is the elevation and the azimuth of the sensor, right? And the noise is, I give it the color purple because it's the most mysterious and regal. It's usually very hard to actually decode. And then you have to, basically it's going to come into some kind of constraint, so that's why it has to be an equation. Right? And throughout this talk, I'm going to come back to talk with you about all of these terms, and I color code them this way, so you can recognize what I'm talking about in this sensor, okay? So for example, this is the ultra-wideband sensor. That's basically the whole PhD research. It's not the whole, but it's like my first chapter or something like that. So if you have an ultra-wideband sensor, right, you have a UAV carrying an ultra-wideband sensor, it can range to this node. What you're going to get is a distance corrupted by noise. And this distance here is basically the Euclidean norm of the position of the UAV relative to the anchor, right? So you have that H equation formalized in this way, and then you measure the distance. You measure the noisy distance here. So that confirms with the equation H equal to 0 I just mentioned. So then you're going to like do some EKF, or you're going to do some optimizations to optimize this number, the estimate of, optimize the number, this position of the position of the UAV, so that your predicted distance matches this measured distance. That's the core principle. And so this is the EKF. This is the EKF. Basically, it's my first paper ever. It's super simple. If you just use ROS, now you just use ROS, you can go get ROS EKF or something like that, and then just fit it, these equations, the Jacobian of how you linearize the observation model, and the rest is job, right? But the mathematics is here, and the mathematics is nice. Okay, so I started my PhD in 2015, and then I told you IEEE came in 2027, so it's like maybe almost 2 years and a half into my PhD. And the first paper was, basically this one is, this equation realized this like type of formation. It's basically, I set up the anchors outdoors, and then we flew 10 UAVs. I remember one day, the chief defense scientist of Singapore visited us. And my professor, he was super excited about showing off this technology. So me and my buddy, we stayed until like 8:30 p.m. in the evening. We tested the 10 drones. It flew perfectly. And there's this thing called the Murphy's Law. If things can go wrong, they will go wrong at the right time. So we actually crashed the 10 UAVs in the real demo. But at least we still have this video here to show you guys that we did it once. It's research, man. It's like a frontier of research. You get one good result, it's worth to show already. But then I for my first IEEE paper, for my first like step into our society, I basically just presented this variant of the observation model, right? And I realized it, and I make it into this kind of, cooperative navigation system with a base moving, and the UAV with like multiple, paths offset from the center, so it couples observation of the it couples observation with the orientation. So that's how you manipulate your H observation function to actually extract more information. If your offset is 0 here, then you don't have the information on the orientation. And then that's actually how I actually reach our society, how I first show up in our society. I would encourage you to be like join this society, because if you're doing robotics, you definitely have to like know about RAS. If you are keen on pursuing further research in computer science, it's computer society. If you're doing control system, they have a control system society. So each society in IEEE will like define your career. Okay. Then that's just the first one, right? It was pretty much like a small exploit of what's well known to do some kind of, demo on the drone. But you see, one night I was talking to my colleague, and then we came up with this, linear observation model. And you see, if you're doing control and then you have something linear, everything can be solved, right? Because you can basically prove the whatever performance you want. And that's why after that night, I actually came out with like 5 papers in a year, because that equation is at the fundamental level. I basically just plug it into a textbook and then prove everything again mathematically and publish so many papers in a year. So I had my Einstein year that year. It's the one thing I didn't show is like the noise. We didn't include the noise in this observation model. It's allowed in research. Sometimes you can ignore something, you prove something, and then you put it into the real world, and if it works, it's valid. That's why we call efficiency and efficacy. We're not always saying you have to be like 100% matching with the reality. Okay. Yeah, so that's my thesis. So basically you can see that equation here translated to this geometry equation. Don't worry about the details. I'm just focus on the story. But the colors, the colors mean to show you what the terms are in my H equation, H, X, Z, M, eta, right? So everything here was here. It's going to be on the video later, so you can actually recall. But what I'm doing is I'm actually exploiting that observation model to actually come up with this kind of joint estimation control law, where you're going to come up with a control law that move around, excite the estimator, and the estimator is going to give the controller an estimate to drive it to the desired formation. So it's a jointly, mutually reinforcing estimation and control law. And that's basically how I organize my thesis here, 5 chapters. The first one here is the IEEE paper that I show you. And later it actually contribute to another autonomous docking paper. And then this kind of advanced, adaptive control contributed to 3 papers. So that's done with a PhD. It's like basically just one equation. You don't have to make like a profound contribution to the field. You basically find new knowledge and organize it into a PhD research, and then show that you can actually deliver the information. So that's the docking chapter. That's actually the most like commercially viable work. You can see that we put the 4 anchors on the platform that is like 50 meters away, and then the UAV can actually estimate its relative position and approach the platform. Once the camera detects the markers, it can trigger the fusion and then do the autonomous landing. That's another IEEE paper in Canada. And this one is on the transactional robotics. That's basically more mathematical. And I call this one my magnum opus, because after this paper, I think there's nothing else to exploit in terms of like ranging-based, swarm. Okay, so my PhD is done. And then I told you the part just now, so you see, I was working mostly on the control side, right? But the perception side wasn't very like prolific. And then, me and my colleague, over my career, we came up with these fuse ponds. So finishing the PhD is nice, but it's basically it's harder than doing a master or postdoc, because for PhD you have to have one theme to last maybe 3 chapters. But for master, or if you go to me and ask me for a thesis, master, it's going to be just maybe one paper's worth. Or if you're doing a postdoc, you can focus on maybe one project, so you don't really worry about the whole theme for the 3 years. And even for professors, they don't actually do this kind of research. They can actually just supervise the students. And what I realized, like, I grow my love for mathematics. You think mathematics is abstract? No, mathematics is the language for you to debug the reality. The reality is like hairy, and there's a lot of distractions. But if you formulate it into a mathematical problem, put in a optimization statement, then you can proceed. There are many solutions for you to solve that problem, but you have to be able to talk about it first. That's why I always hate reading papers in machine learning venues, because every time they're going to make you interpret this common term in a new way. A head, it's basically just like another layer in the neural network, and then they call it a head. Why? They just call it another a layer, right? And I was very lucky to file that equation to cook up my thesis. And I was telling you that working on the control side is a privilege, but you still have that, mysterious area of sensors that I actually didn't explore thoroughly. And we have this kind of meme where I think I started here from control, but some of my colleagues, they started from mechanical, and we have this kind of like infatuation with the next step in the cycle. Right? The control people, mechanical people, they would fall in love with control very easily. They would want to like model something and then put up a control on it. Controllers, we are fed up with control. We say control is basically just numbers on the equation. You want to do something with the sensors, so we go do SLAM. Once you do SLAM, then you realize that you need more information to like do machine learning, right? You want to like do machine learning, and then you want machine learning, and then people think about, now we have this foundation model, LLM, VLM, that is very famous, and then people try to like make it into robotics, so they invent a new word called the embodied AI, but it's actually just like robotics. Embodied AI is just robotics, and then embodied AI people now have to go find new bodies to embody their AI in. That means they have to go back to mechanical engineering and build new robotics, new robots. So I kind of find myself already going on this circle for 3 steps. Where are you? Now mechatronic people already started somewhere here, I believe. But you have all the loop to go back to find yourself in mechanical. Okay, so for the next chapter in my research, I focus on the sensors very deeply, and you can see that we built this, we call it the anti-viral drone, because it has visual, inertial, where's the IMU one? Yeah, ranging, so all of the ultra widebands, and then the LiDAR. It's also happened at the same time with the COVID, so I don't know. I call it the anti-viral because so it has all of the sensors here, and what you do here is like I exploited that observation. Actually, I only like conceptualized that observation model at this stage of my research. I realized that all of the sensors actually have to follow that framework, and this is a very complicated SLAM system. If you've done SLAM, you know that you have to like worry about synchronization, how to like remove the noise. This camera, it's going to need a filter when it works in the sunlight, or it needs autofocus or something like that. You have to turn off the autofocus sometimes to make the frame rate consistent. So all of the sensors, I actually had a freedom in the postdoc, so I actually went very deep into all of the sensors. And then I realized the equations are actually the one that matter. And yeah, and then each of the observation function is going to relate to one sensor, and then what you do is you're going to write you're going to formulate the difference between your observation function and the one that you plug in your estimate, right? So you plug the two in, and then you find the difference. That's the core principle of the estimation, and then you write this cost function, and then you try to optimize it. And this is my first paper to actually formulate this one. For example, if you're talking about LiDAR, did Tyson teach you how to do SLAM, or he just like measure something? Just measure something, right? I think it's just measure something. But like if you're talking about LiDAR SLAM, you're going to get the first LiDAR scan to be your first initialization of the map. Then the next point cloud, you're going to reference to this one. The next point cloud reference to this map. After 1 meter, you put the point cloud into the map to grow the map eventually. And the key point is you're going to have this point here that is going to be coupled with your robot pose. And then you're going to have the map, and then you're going to calculate some kind of surface parameters. So that's the prior. And then you put into this equation. So that's going to be your observation model.
So you might be able to just like explain, just like a quick explanation of like what
SLAM is
yeah, just like for base, like just for understanding as well.
Okay.
Yeah, you might not understand what a point cloud is, because I don't think everyone here is continues to like LiDARs.
You know the LiDAR, right?
Yeah.
I have a LiDAR here. It's going to give you the map of the surrounding. And basically, you want to move around in this environment, and then you want to estimate your position, right? So I put a LiDAR here. It's going to get the first scan of this environment. Then you're going to move for maybe 1 meter, right? then this point cloud is going to shift relative to the first point cloud, and then they're going to do the maths to estimate the displacement, right? So that's the key principle. And I'm telling you, these, these blue points are the points in the map that are going to be compared to, okay? And the principle here is not to understand this equation. The principle here is to recognize the pattern of like how you always come up with these x, z, m, and eta in your observation model, right? And that's like basically your doctrine, your principle. If you handle a sensor and then you don't fall back to this one, you're going to get lost. And that's what I want to introduce here. Then, okay, maybe I can skip on the details of this, like how I do the SLAM here. But basically, there's a this is if you go to me and do SLAM, I'm going to like knock on your head and then tell you to do these 4 steps, right? It's like the 4 noble truths, and you have to be a monk to do this so many times to actually realize that these are the 4 steps you keep doing. Yeah, so basically we did the SLAM, and then you can see the SLAM is basically giving you the position of the robot in the space. With this position, what do? You fly around, you move around, and then your movement is going to generate value to the operation. For example, we use in our one project, we use this drone to inspect the facade of a building. You want to detect you want to fly in front of the facade. It's a degenerative environment, it's flat, there's no feature. So you want to fly there and then detect the cracks and the patches of paints that need to be repaired. We also fly in this crane area, in the seaport area, with all of the cranes. Flew next to the airplanes to actually inspect the surface also. See if they lose a nut or something, you have to find it out. And then I published a paper on this data set also. So, and I also I also created this course on SLAM for the PhD students. It's quite intense, but everybody enjoyed it at the end because they negotiated the number of credits. Okay, so for the continuous time optimization, so maybe we just go quick on this one. As you can see here, we have so many sensors here, and if you go look into the SLAM courses, do you know who is the most famous on SLAM? So it's like if you go find David Scaramuza in UPH in Switzerland. You also have Shan Xiaojie in HKUST. Those professors, they work on SLAM, so basically they're master of this. And most of the time, 90% of the SLAM system use this kind of discrete framework. Means you have to find a synchronizing signal to determine the state, okay? And then I realized that this kind of thing is going to make it very difficult because you see LiDAR is basically 1,000 points in a 0.1 second period, okay? MU is like 400 hertz or something, okay? Ultra wideband is like 80 hertz. Images is 10 hertz. So it's like all of these sensors come in at different times, at different frequencies, and then you have to every 100 milliseconds, I have to create a state and then observe all of the states and then formulate an optimization problem. This one is very tedious, right? And it's also very brittle. For example, in this case, I had to use a sensor with the lowest frequency, which is the LiDAR, which is the camera, to do that kind of synchronization. So if the camera goes out, I'm screwed because all the sensors will lose the synchronizing signal. So 3 papers in, I came up with this slide. You guys also don't understand at all, I believe. But colors, okay? I'm trying to show you the crayons, right? Basically, the colors here. I'm not trying to introducing new mathematics. I'm just trying to use that at the end of the day, the X, the Z, the M, and the eta are going to always appear in your sensors. The sensors have to answer these. All of the sensors have to answer these, right? And continuous time means I'm going to basically say, okay, this trajectory is going to be a polynomial, for example. Don't look at the slide, look at me. It's going to, if the sensor comes at this time, then I can determine the X at that time based on a few parameters, that's all, right? So you don't have to worry about a sensor giving you that signal You don't have to have that sensor that is giving you the authority to choose a new state at that time, right? So that's, and then I came up with the 3 papers and I came up with this framework to do that kind of continuous time formulation. And at the end of the day, you can realize that basically it's also conforms to the 3 colors that I mentioned. I mean, the time shows up here because nobody cared about the time before. Okay, so this slide is like how I presented myself to the recruitment committee in UQ. Basically, I started my first SLAM paper in 2021. That's the discrete time one, and then I moved on to the first one with continuous time. I call it the Fellowship of the SLAM because I was in KTH, Sweden, and then I collaborated with a colleague to combine the continuous time formulation with his line mapping framework. Then I returned to NTU, and then I fixed the problem of this one by redoing the solvers. I compared a solver with my own solver, so I call it the 2 solvers. So this paper, then after doing this one, I realized some technical mathematical issue with the polynomial framework. Then I moved on to the Gaussian process. But the Gaussian process was like maybe 10 years ago, but they had something they haven't finished, so I finished it. And I call it the return of Gaussian process. So basically you have a whole, lot of the SLAM here, trilogy. And this paper here just got accepted. I mean, I started 2 years ago, now it just got accepted when I joined UQ. It's on the transaction of robotics. Oh no. So, and then finishing that paper means I'm already kind of finished. Every time I do something, I do 3 papers and then I think it's done. Because I don't want to overdo the thing. I want the community to continue further. Because if you keep doing the same topic over and over, you kind of like, you don't grow as a person. You want to move on to the new, more challenging problems. But what I'm trying to show here is like, every time I do something, I do 3 things, and those 3 are supposed to be impactful. And how do you measure the impact of a research? Basically, you say, okay, it comes out, who cites it, who references it. And so those papers are basically mentioned in some of you. For example, I didn't have that slide here. Yeah, but that one I was cited by like CMU and ETH and Beijing, Tsinghua. Yeah, so basically internationally recognized. Maybe that slide later. So now the second one is about the prior. So you see, we've been focusing on the state and the observation. Now what I mean is like the prior. Just now you say there's a map, right? So that's why I choose the letter M for the map here. And this is what I call a multi-campus data set. This work I started in Sweden in 2022. Sorry, I started in NTU Singapore in 2021. Then I continued in 2022 in Sweden, and I returned to NTU. So that's another 3-year project. And basically we had we mapped the 3 campuses. We mapped the 3 campuses in in the whole Eurasian continent. And then we provide, comprehensive data set. And then I combined it with my continuous time estimation to invent a new ground truth. I usually say this: you can strap a camera on a dog, let it run around, capture the data, and it can be a data, but it doesn't make a data set because the value of the data set is not in the data. You know what is the value of the data set? Dominic? It's in the ground truth. The value that you add into the data set is how human intelligence is captured in the ground truth. Right? So basically, I orchestrated this scheme where I have to like compare my LiDAR scan with the survey map to actually come up with the ground truth. And then the other type of ground truth of machine learning is where you actually use a human intelligence to tell whether this is a rock, this is a tree, and you annotate them. So I remember me and my buddy, the 2 PhDs with like 7 years of experience, we were arguing about whether this chunk over there, is it a rock or is it snow or is it something else? Right? But that process captures the prior knowledge into the data. Yeah, so you can see the campus here. Basically, it's a flyby. It's huge. It's basically, I think our campus. This map is about 1/5 of, maybe it can be like the Foggen-Smith, the size of Foggen-Smith, the size of a loop around Foggen-Smith. And then you see the color here, that's from me coloring them. one by one. And I remember it was very meditating. You have to go, hunt for people that got captured into the data set, and then you have to delete them manually. I spent maybe 100 hours for the first sequence, and we had something like 6 times 18 sequences. 100 hours for the first one. So after I finished that 100 hours, I could convince my colleagues that this is doable, this is humanly doable. Right? Then actually they jump in with me, and then that's me and my colleague arguing whether this is a rock or this is snow. Yeah, so the data set is like capturing, it's very nice. I studied capturing the data in Singapore in the middle of summer, and I went to Sweden, it was in winter. So I remember one sequence, we captured the data at 4:30, we finished the loop in 10 minutes, and the sun basically just disappeared. It was like bright as a daylight, and then it's like pitch black. And then it was nice. It was autumn in Germany at that time. It was nice. So this data set, how do you show that the data set has like research value? What we do is we use a machine learning model to do this kind of semantic segmentation. So we're going to put the data through, and it's going to show you that there's like a 20% gap in the recognition of the classes. So say, okay, there's this big gap. The other data sets, the community has been doing it for 80% accuracy. Now, after I train your model, I put it into my data set, I only have 50%. So there's like a 20-30% gap. So everybody, let's do research with this one. So that's how you show there's the value in your data set. And then another one is like another kind of idea. Basically, when you travel in the campus, right? You travel on the fixed road. And then what I thought was, okay, let's just put some beacons in the environment, and then when you travel around, there's going to be a pattern. And then you're going to see the observation to the sensors the same way. So where is a pattern? There's a machine learning. Right? You slap machine learning on it. Basically, if there's a pattern in it, you slap machine learning on it. And then what is machine learning? Machine learning is basically also just, you're going to have some observation, you're going to have some ground truth, and then you want to estimate the parameters of the machine, of the learning model. It's the same thing. It's always x, z, m, eta in different forms. And you optimize, the optimization is another thing. I'm going to teach you like robotics in 2000. I mean, if the powers that be allow me to teach, I'm going to like talk about optimization here. What else? Yeah, so this one is that one is the, how I navigate in this prior map using this kind of like pattern of the ranging signals. Okay, and another work that doesn't use that beacons, it just uses the LiDAR features to just basically give you one point cloud data and the prior map, and it tells you where you are in that map. Hopefully, I mean, there's a 1 meter tolerance of error for that kind of thing. So we call this one a one-shot localization problem. Right. So yeah, this campus data set, it's basically 2024, 2026, and you can see it's been cited by transaction robotics. I'm biased towards IS, so there could be other places. This one is from ETH. This one is from Japan. Yeah, so basically 2 years, and this is the much impact because I don't think anybody is crazy enough to go argue about the rock and snow in their postdoc time. It's very valuable time. So for future work, exciting. What I'm going to do is like as I've seen the field so far, I realize that okay, we've matured in terms of like localization and mapping. SLAM is mature. I can guarantee you that. You can buy off-the-shelf sensors now to walk around the campus, and that gives you this kind of map. Can you see this kind of map? It's very authentic. You can read the letters here. And then we have this AI boom in recent years, and then in NVIDIA, they've got a lot of money to put into the physical AI movement, so they come up with open source. They actually created this thing called the Isaac Sim. It was closed source from the beginning, but now they've handed over to the community. They open source the development, so the community is actually putting effort into that one. So what I think is like we are going to digitize, I'm going to digitize UQ, put it into like a simulation environment, and then you can basically teach you can synthesize new data from the environment, and then put a robot into this environment so that it can learn, and then it can imbue the knowledge of the environment. For example, if you are familiar with UQ, right? I meet you at the Chancellor's place, and I'm asking you to take me to Mansard Shore. You're probably going not to like open the map and then draw something, right? It's going to be subconscious. It's going to be like this view next after this view. So this process is embedded in your intelligence already. So that's what I'm going to try to achieve. And then we're going to have a real-world deployment. I already bought the. This is so on the first ingredient. So you can see this digital twin. Do you see? This one is actually a digital model. It's my campus in NTU. You can actually move around in this environment, and it's almost like a game. Right? It's actually more real than a game. The game, you always see some kind of plastic surface, but this kind of technique now is very authentic already. And this is my plan for this year is to map this loop here, so you're going to have another digital twin of UQ. So that's the first ingredient for my vision. It's still like starting. The next one is my robot dog. I bought this one. It's named QQ. You know what? Because it's QQ, but I'm going to build another robot. I'm going to build another UAV, and the UAV is going to be called the UU. So you're going to have a UQ sibling. And this guy is like, this girl actually is running around just nice, and I've successfully put a computer on it, and then I've deployed some policy. So this is some kind of policy that you can do so far. But later it's going to have the intelligence. This is just locomotion, moving around, using its own sensors like the encoder and the IMU data. So it feels, it's called the proprioception. Later we can, if you use LiDAR and camera, it's called exteroception. Okay, so that's all, almost done. This is the last slide. So it's 1 hour, 50 minutes. But like, that's my journey so far. And then you can see that basically I've been going through a lot of research. And then if you think about like doing multi-robot system, that's what I did from the beginning. Then other thing is the sensor. Right? Basically, I've had so many sensors for breakfasts, I cannot count anymore. But at the end of the day, all of the sensors to me are just equations in different forms. Right? So I hope after today, when you come home, you can realize, okay, you don't have to worry about this sensor or that sensor per se. You just say, what is the mathematical equation? And then you start exploiting it. And then, so the next journey, I've been working with UAV a lot. I'm basically a UAV guy. I have friends who's working in DJI. They give me intelligence about like US boycotting DJI, something like that. But that's for another thing. But the next few years, I'm going to focus on the ground robot and the learning side of the robotics, not just model-based anymore. And so if you're going to fight me on RAS, you see, these are not realistic. I mean, but these are the main keywords. Okay, thank you. Any question? I think this one was meant to be for the UQ robotics seminar, but yeah. But I guess sometimes you have to see the sky to actually aim for that high, right? Any question?
With digital twins, like, what's like the brain behind like the robot? Would that just be like another neural network or something?
Okay, yeah, good question. Digital twin is defined differently for different people, right? So if you talk about factory automation, they would be happy to have some kind of, sensor collection and then reporting to the human. That's already enough for them. In my work here, the digital twin that I'm going to do is exploiting things called the 3D reconstruction So the key word here is 3D reconstruction. It can be based on classical structure for motion. It can also be based on 3D Gaussian splatting. It can also be based on the neural radiance field. Neural radiance field is the neural network. What you say? This one is that. This one has already been superseded by the 3D Gaussian splatting. So this 3D Gaussian splatting is the latest technique now. And it's basically models the environment by a bunch of, parametric Gaussians. And it's going to optimize, there's going to be a H function that is going to mix the color and the position to actually optimize that parameters. Yeah.
And when you use these 3D reconstructions, when you simulate it on your computer, do you need to be able to simulate the physics of how the robot would interact with the environment?
It's different from the physics, yeah. So it's going, the 3D construction, the 3D reconstruction is going to give you authentic novel field synthesis. So basically, for example, I'm going to build this room using 3D reconstruction. If I put myself into another position, I should be able to get an image of very high quality. Right? If you have a phone, you can take a snapshot at individual spaces. But if you make a model of the room, means you can interpolate between them, and then, but you wouldn't have the ability to touch. That would need another model. They can coincide, but they don't necessarily be the same one. Yeah. Actually, in this one, you can see this one is for that visualization. This one is for that reconstruction. This one is actually exploiting the physics. This one is putting the whole point cloud into the environment and then generating a mesh so that when the robot lands its foot on the ground, it's going to generate some contact physics with the ground. Right? So that's the physics side. Yeah. Yeah. Exciting? Yeah. It needs something like a 5080 GPU to do that kind of thing. But now is actually a very good time to do this kind of thing because NVIDIA is behind it. I don't usually buy into the, billionaires talk like Elon Musk telling about everybody to do humanoid. It's OpenAI telling people, oh, it's going to have the, general intelligence. That's not exactly helpful, but I believe the physical AI is real. That movement is real because we've never had this kind of big models to play with before. Robotics is actually having this kind of springtime. That's why I'm hired, actually. The story I heard is that some students wanted to do robotics in UQ, and they talked to the vice chancellor, and then the vice chancellor say we don't have big, strong robotics program, so they're actually reforming mechatronics engineering. Dominic, are you there? Were you there in the? Yeah. We're adding robotics into mechatronics, and they're going to put in 4 more courses next year, something like that. They're going to have introduction robotics, mathematics for robotics, SLAM, autonomous driving, maybe. That's a lot. Yeah. Any question?
All right. Well, if there's not any further questions, thank you for coming along and chatting to us. As you may or may not all be aware, we've got food happening just outside, so you'll be able to go out and eat after this. I believe we have one more talk coming up next week. Not sure if the details are out yet. If they're not, they will be shortly. So look forward to that one, and that'll pretty much see us through our academic events for the semester. But otherwise, that wraps things up. So thanks again for coming and chatting to us. I'm sure if anyone has any questions there, you're happy to take them once we've wrapped up here.
Yeah.
Wonderful. Otherwise, thanks for coming, everyone, and we'll see you all next week.
Yeah. Am I?